Hello, I am Srinidhi Kukila. Welcome to the third session of Flight Vehicle Performance. The topic of discussion in this session is lift enhancing devices. So we are going to discuss in this session introduction to the devices, passive lift enhancement, lift determination, drag determination, and active lift enhancement. Introduction. So lift enhancing devices, the value of maximum lift coefficient were used to determine the takeoff and landing distance. These assume the use of some type of lift enhancing devices. Such devices provide a methodology for determining the three-dimensional lift and drag characteristics in a high lift configuration. The goal is to achieve necessary maximum lift coefficient values in order to satisfy the maximum lift requirements that are imposed by such flight phases as takeoff, landing, and maximum maneuverability, that is during combat. In a 2D wing, the lift at a given angle of attack can be increased by increasing the camber. However, the maximum achievable lift is limited to the amount of camber or the angle of attack at which the now can no longer follow the curvature of the airfoil and separates. In most cases, when this occurs, the flow separates first and the leading edge. Lift enhancing devices fall into categories: passive and active. The passive devices also fall in two categories: trailing edge devices, which primarily act to increase the camber of the airfoil section, and leading edge devices, which primarily act to prevent leading edge separation. Passive lift enhancement is relevant to most of the aircraft designs except short takeoff landing and ultra short takeoff landing. Such designs must make use of active lift enhancement. This generally consists of using airstream that are directed over the upper surface or wing in order to energize the boundary layer and prevent flow separation. Passive lift enhancement. So this is the schematic illustration of different trailing edge flap configuration. The most common types of trailing edge lift enhancement are plain flaps, split flaps, Fowler flaps, and slotted flaps. Slotted flaps include single, double, and triple segments. So these are the different flaps in trailing edge. The most common type or leading edge devices are fixed slot, leading edge flaps, Kruger flaps, and plain slats. So this is illustrated in of different leading edge flaps configuration in the screen. The plain flaps is simple, a deflection of trailing edge of the airfoil section. This type is most widely used on smaller aircraft. The split flap is similar to the plain flap except that only the bottom half of the airfoil section deflects. The lift produced by a split flap is virtually the same as plain flap, but the drag is larger. A slotted flap is essentially a plain flap with the addition of a slot at the hinge point to allow high pressure air from the lower side of the airfoil to pass over the upper surface of the flap. This has the effect of adding momentum to the boundary layer or the upper flap surface to allow larger flap deflections. before the flow separates. A Fowler flap is a slotted flap that translates rearward, away from the wing. This has the benefit of increasing the slot width and increasing the effective wing area. Further refinements of the Fowler flap design involves using two or three flap segments. This design can lead to extremely high lift coefficient of around up to 3, but are complex and require extra volume inside the wing to be stored during cruise. Single slotted flaps are most common on mid-size aircraft. Most larger commercial and transport aircraft use multiple slotted flap arrangement. Although trailing edge flap increase lift at a given angle of attack, they do not increase the stall angle, that is alpha s, but actually causes it to decrease. This is the result of changes in the location of the stagnation line and local pressure gradient near the leading edge, which leads to the leading edge flow separation. Sharper leading edge are more sensitive to this. One solution for leading edge separation is to increase the leading edge radius. This is the principal effect of a leading edge flap, which generally consists of a hinged portion of the leading edge, which deflects downward to effectively increase the leading edge curvature. A variation on this is a Kruger flap, which consists of a hinge flap on the lower side of the wing leading edge, which extends out into the floor. This approach is lighter in weight and as a result popular on large aircraft with large wingspans. A leading edge slot works the same way as slotted flap, but allowing air from high pressure lower surface to flow to the upper surface to add momentum to the boundary layer and prevent flow separation. Of these devices, leading edge flaps are more effective than slotted flaps on highly swept wings. They are also usually located over the outboard half span of the wing in order to reduce the potential for wing tip stall. The optimum leading edge flap deflection is up approximately 30 to 40 degrees. Lift determination. Lift determination is the approach to construct the 3D lift coefficient versus the angle of attack for the main wing with flaps and slats. It involves determining the changes in maximum lift coefficient, zero lift angle of attack, and stall angle that result from these passive lift devices. Additionally, the added drag due to the lift enhanced lift configuration is calculated so that it can be compared to the empirical value used in the takeoff and landing analysis. The effectiveness of any of these passive and active devices depend on their deflection angle delta f, the wing thickness to chord ratio T by C, the ratio of flap chord to wing chord CF by C, and the wing sweep angle and aspect ratio. In most cases, the ratio of flap chord to wing chord is approximately 0.3 and the maximum lift occurs at a deflection angle of 40 degrees. Starting with the original 3D lift coefficient versus angle of attack that was previously developed, the first step is to find the change in the angle of attack at zero lift, that is delta alpha naught L is equal to minus dCl by d delta f into k dash by CLA into delta f. where the term dCl, derivative of Cl by delta F, is the change in the two-dimensional section lift coefficient with flap deflection. K dash is a correction for nonlinear effects. CLA is the 2D lift coefficient, which from linear theory should be around 2 pi per radian, and delta F is the deflection angle. For single slotted and Fowler flaps, delta alpha naught L is equal to minus d alpha by d delta F into delta F, where d alpha by d delta F is the function of the ratio of flap chord to wing chord, and alpha is the angle of attack. For split flap, delta alpha naught L is equal to minus K by CLA into delta CL at CF by C is equal to 0.2, where K is a coefficient for determining delta alpha naught for a split flap. For finding maximum lift coefficient CLmax requires determining whether the main wing in the design has a low or high aspect ratio. This distinction is made because with high aspect ratio wings, CLmax is primarily determined by the airfoil section shape, whereas for a low aspect ratio wing, CLmax is primarily determined for the wing planform shape. A wing is considered to have a high aspect ratio when aspect ratio A is greater than 4 by Cl plus 1 into cos gamma Le. The coefficient Cl is a function of the taper ratio lambda. For high aspect ratio wings, CLmax, maximum lift coefficient, and stall angle are found to be CLmax is equal to CLmax by CLmax into CLmax, where uh, and alpha S is equal to CLmax by CLA plus alpha naught L plus delta alpha CLmax, where CLA is derivative of CL by A is for basic 3D wing, the stall angle alpha S, and the only parameter not already determined is delta CLmax. This can be obtained by the graph, which is the function of leading edge sharpness parameter delta Y. Next is low aspect ratio. For low aspect ratio wings, CLmax and alpha S are found to be CLmax is equal to maximum lift coefficient of base plus change in the maximum lift coefficient, and stall angle is given by alpha CLmax of the base plus change in the alpha CLmax, where CLmax is a function of sweep angle, aspect ratio, Mach number, and coefficient C2. Next is the lift determination. So CLmax for 2D flapped wing then approximately corresponds to the lift coefficient at stall angle with flaps. Alpha S flap is equal to alpha S base plus change in alpha S, and change in CLmax is equal to CLmax during flapped wing minus CLmax basic without unflapped wings. Next is drag determination. When the trailing edge flaps are deflected, they produce an increase in the base drag of the wing, that is during zero lift. This is expressed as an increase in the base drag coefficient, which is given by delta CDO is equal to K1, K2, SWF and SW, where the coefficient K1 is a function of the ratio of the flap to wing chord for the different types of flaps, and the coefficient K2 is a function of flap deflection. The value of delta CDO should be added to the base drag coefficient CDO for the main wing in order to calculate the overall drag at takeoff and landing. So with this you can determine the total drag or overall drag. Next is active lift enhancement. Some of the common approaches used for active lift enhancement fall in three categories: upper surface blowing, blown flaps where air is supplied either externally, or external blown flaps, or internal blown flaps, and the third one is vector thrust. You can see this in the image in the screen. That is examples of activity lift coefficient approaches. When upper surface when upper surface blowing when upper surface blowing, a high velocity airstream is directed over the upper surface of the main wing. This requires placing the engines above and forward of the wing. With blown flaps, high velocity air is directed specifically at the trailing edge flaps. For external blown flaps, the air is supplied by the engine exhaust and the engine is located below the wings. The flaps are slotted in this case so that high momentum air can reach the upper surface and energize the boundary layer over the flaps. The portion of the air in this arrangement is also deflected downwards. Internally blown flaps (IBF) duct a portion of the engine exhaust air only to upper side of the trailing edge flaps. Vector thrust uses an articulated exit nozzle to direct the jet exhaust air downwards. This gives a downward component of thrust which is independent of any aerodynamic lift enhancement of the wing. In addition to the enhanced aerodynamic lift that these three approaches provide, they also generate a component of downward thrust. This results because of the Konda effect, which is the ability of an air stream to follow a curved surface. When properly designed, the airstream on the upper surface leaves the trailing edge at the angle of the flaps. In all these approaches, there are the effectiveness of these active approaches is summarized in terms of drag polar, that is CL and CV. Any of these capable of providing lift coefficient is excess of 7.0. The vector thrust, USB and IBF have lower drag coefficient than EBF, externally blown flaps. Also, the effectiveness of USB is a function of a jet coefficient defined by the ratio of thrust divided by Q into SW. In all these approaches, there are additional factors that affect the selection of one over the another. The internally blown flaps require internal ducting that can be heavy and result in internal momentum loss. The upper surface blowing the upper surface blowing blows hot exhaust air over the wing surface. So this generally requires that portion of wing to be covered with a heat resistant material like stainless steel, which adds weight. The externally blown flaps approach only directs the hot exhaust over the flaps so that the area of heat resistant material that has to be covered in less than with the up USB. This makes the weight penalty less. This and its relative simplicity may be the reason that the USB approach appears to be the most popular means of active lift enhancement used by aircraft manufacturers. So these are the things we discussed in the session 3 of flight vehicle performance, that is introduction to lift enhancing devices, passive lift enhancement. Through passive lift enhancement we have studied lift determination, drag determination, and then the concept of active lift enhancement. If you have any suggestion, doubts, clarifications, please comment below. Thank you.